Boeing 777 was actually the first airplane, which was designed now 20 years ago, designed entirely via computer-aided design before anything was built. In fact, they sent sort of a famous story. They designed all of the parts and then sent the plans off to tool and die companies and got all of the pieces, 6 million pieces, and brought them all into the Boeing warehouse. And then assembled the plane without having tried anything and without having put anything together. We just built all the pieces, brought them together, and started screwing them together, and then the plane did fly. So that's a picture of the 777. There were 3 million separate parts. So you can compare this now. The reason to talk about that is not that it's anything you don't know. It's just to remind you. And to get you to think a little bit about the degree to which we are designing things before doing them for most complex objects in the real world. Chemistry, on the other hand, this is what things look like, right? So this is actually a synthesis from one of my colleagues, Paul Wender, for bryostatin, and this was not designed computationally in any way. This is basically just trial and error. Right, and so you just take a bunch of molecules, stick them together, see what happens. For some new molecules, of course, they're very, very smart, so it doesn't take them forever to do this, but it still takes quite a bit of time. And it's in striking contrast, really, what we're doing at the atomic scale, I would argue, as a field, is in stark contrast to what we do at the macroscopic scale and the mesoscopic scale. And really, I think that it's time. I think that I'm not the only person to say this. That it's time really to start to change this and really to start designing things at the molecular scale. And as theorists, there's been much emphasis on explanation. So on how is it that if I have some experiment, I want to understand what that experiment is doing, I can do some calculation, devise some theory, do some simulations, and actually begin to understand what's really happening to give rise to the particular effects that I saw that some experimentalists saw in the experiment. But there's been a lot less prediction, a lot less emphasis, on the last two pieces of this, which are part of what I would consider as a cycle. I mean, the first part of the cycle is that you should be able, with some theory and simulation, to explain what you see. But the second is that if you actually can do that well, then you should be able to now begin predicting things. And predict here should mean predictions of things that you don't already know. So not confirmation, but prediction. And once you know how to do that, then you should be able to design things. And the question is, what do we need in order to do this? What do we need in order to take theory and computation and make it really capable of doing that? And this is, one of America's favorite philosophers, and his statement about why that's going to be hard. So. Then the question is sort of what to design. And here, I really don't want to go into a lot of detail about it. These are things that I've been interested in. You would like to be able to design environmentally responsive materials. So to take polymers and make them such that they had certain chemical responses to force. This is a particular case of a molecule that we were involved with in collaboration with the Moore group, which at the University of Illinois, which basically when you take this polymer shown here and pull on it, so you put this into a solid state polymer and pull on it, then what happens is that the spiropyran, this spiro bond here, tetrahedral carbon bond, breaks, and you make a merocyanine dye, and this goes from being transparent to being red, and you can see here the stress field essentially after the molecule's been broken, right? So how would you make other molecules which are mechanosensitive and which do reactions that you might be interested in response to this mechanical stress? How can you design reporters that would, for example, fluorescent proteins that could be used in optogenetics or they could be used in bioimaging that would be able to actually show via light, fluorescence, or absorption what is going on at the molecular scale in living things, in cells. And how do you build better photovoltaics, better batteries, better fuel cells? All of these things really require something that is super important, and that is they require the rearrangement, they require electronic structure, they require to be able to describe bond breaking and bond formation. right? And that's sort of the key. And the size of the molecules involved in all of these cases is going to be in the hundreds of atoms and beyond level, right? So because to get that kind of complexity, that's what you're going to need. So that's what you would like to do. And I don't want to belabor any of the particular applications, but say now, why is this hard? And that's foreshadowed a little bit by what I was saying. It's hard because the equations that we need to solve are quantum mechanical equations, right? And so even explaining is difficult. If we want to predict, then we have to actually layer on top of that the problem that there are many, many molecules, there are many possibilities, there are many explanations, and we're going to have to be able to exhaust these. And to give you a sense of that, you can just go back to to give you a sense of the complexity. You can sort of step back and say, well, if I was going to start searching over molecules to be able to predict function, for example, then I'm going to care how many molecules there are in the design space. And the number of medium-sized molecules is 65 million. The number of the estimated known medium-sized molecules, known. The estimated number of actual sort of drug-like molecules, again, sort of medium size and having certain properties that we don't care about right now, is 10 to the 60. The number of atoms in the universe is about 10 to the 60 or 10 to the 65, right? So there are more unknown molecules than there are atoms in the universe, or at least of the same order of magnitude. All right, so what are we going to do? So in order to get to go at this, we're going to start with an approach that allows us to solve at least the chemical part of the problem. That allows us to describe bond rearrangement, allows us to describe electron and proton transfer, it allows us to describe excited electronic states. And that means we're going to solve the Schrodinger equation. We're going to couple the solution of the Schrodinger equation to the solution of the dynamics equations for the nuclei. So we'll answer these two questions. Where are the electrons and where are the atoms? And we'll answer them together, right? This is first principles molecular dynamics or ab initio molecular dynamics. And we can do this for classical mechanics. We can do this for the nuclei. We can do it for quantum mechanics of the nuclei. Why is this a problem? Well, the problem here is that it's hard, right? So I just said, all right, we're going to do this. We're going to do it lots of times, but it's very, very difficult. And an example of how hard this is something from about 10 years ago now, where basically they took a protein in solution and did a calculation of a single point energy. And the amount of time it took to do this was 2 hours on 8,200 processor cores to get just the energy. What we're going to need is dynamics. So we're going to need to do this over and over and over again. We're going to need to do it for many, many molecules. So this is going to be a problem, right? It's going to be a big problem. So what we turned to some time ago now, in order to try to solve that problem, was video games. What we noticed was that video games were getting better and better, and they looked a lot more realistic today than they did when I started working on them, when I started playing video games, that is, in 1980, which for most of you is probably before you were born. But at that time, this is what video games looked like, and I thought they were fun. But now they look like this, right? And so something really happened over that 20, 30 years. And what happened was that computers got faster, but even more than that, what happened was that many, many people wanted to play video games. And so they put a lot of money into it, and they made them they made the machines that played the video games, that you'll play video games on, much, much better. And then ultimately this led to graphics cards, which now are in high performance computers. So we took quantum mechanics and we put this on graphics cards. And the final result of that was essentially 100x speed up. So you could now do electronic structure about 100 times faster than for CPU. And that's sort of where things stand. Like I said, I'm not explaining this to you, I'm just giving you this as background. So now calculations on molecules with hundreds of atoms really can be done in seconds without any problem at all. But this led us to a problem, right? And this I will tell you a little bit more about. And the problem was that the GPU was still not enough, so it still wasn't fast enough. So 100 times isn't what I need. I need 10,000 times, right? So it's speed up, right? Or 10,000 times more efficiency. So how do you do this? And so here, I want to give you a flavor for the kind of idea that could make things better. And let's just go step back and say, what is really the problem in quantum chemistry? So in quantum chemistry, you have electrons and electrons interacting with each other, and that means there's going to be Coulomb repulsions, right? That means you're going to need some integral of a charge density of electron 1 and electron 2 interacting via the Coulomb force. And because it's quantum mechanics, you're going to end up with basis function products, which give rise to each of those charge distributions. So some label I and J, which describes the charge distribution for electron 1, some label K and L describing the charge distribution for electron 2, and this is the integral that we're talking about, which is just Coulomb. The wave function itself, now I can think of that as a tensor or as some object which has 4 indices, right? The wave function itself is going to be written as some expansion over products of over determinants, over products of orbitals, and they're going to have numbers in front of them. Those numbers also are going to be, these wave function coefficients are also going to be tensors of some kind. They're going to be objects with multiple indices. So I have 2 indices for this, the coefficients of the single excitations. I have 4 indices for the coefficients of the quadruple excitation, the double excitations, right? And then what the problem is that I'm going to have to manipulate these tensors. So I'm going to have lots of objects which are arrays, if you want, with 4 dimensions or even higher, and I'm going to have to manipulate them, and then I'm going to have to contract them, right? So I'm going to have to take sums over these. And the question that I want you to just have in your head right now is, do these tensors actually have as much information as they seem to have? So if I have a matrix with 2 dimensions, there are n elements on each side, then there are n squared pieces of information in that matrix, apparently. But are there really n squared pieces of information in that matrix, or are there redundancies, or are there zeros? And that's actually the question to ask yourself when you see this. So I would just say here, there's lots of numbers. Do I really need to worry about all of them, or am I just wasting all my time? Right, and that's really the question. So to give you a sense of how we approach this, what we did was we started to think about recommendation systems. So you probably remember this. Certainly you know this in Amazon. Whenever you go to Amazon, it asks you whether you want to buy something. And if you use Gmail, it's probably constantly sending you emails about, or showing you in your email, maybe you want to buy this other thing. If you use Netflix, you know that if you want to watch movies, it will actually, or if you watch movies on Netflix, it will start recommending things to you. And how does it do this, right? How do recommendation systems work? And this is the way they work. So you have essentially a matrix, and you'll see in a minute this relates right back to this tensor problem. So you have a matrix. Let's talk about movies, where I might have several movies that I might have in my list of movies that I could recommend to people. And I have several people. And then for each of these people, I have an entry, right? For every person, movie combination, I have an entry. And that entry tells me whether or not that person likes that movie, right? So Joe here, doesn't like Dark City. He's never seen Star Wars. He kind of likes Zero Dark 30. He doesn't like Steel Magnolias and so forth. Fred loves Dark City, loves Star Wars, doesn't like Zero Dark 30. And then there are question marks, right? And the question marks are places where the system has no idea. It doesn't know, right? So it has no idea whether you like that movie or not. You didn't watch it. You didn't hover over it, right? It has no idea. So what your task is to complete this matrix. And by that, what I mean, your task is to actually take each of those question marks and put a number in there. So the assumption is that Joe does have some opinion about Star Wars. You just don't know what it is. And I want you to predict it for me. So is it possible to do this? So I give you a matrix that has n squared elements, and then ask you to, and some of the elements are question marks. Is it possible to simply reconstruct the question marks? And the simple answer to this is, in general, no, right? It can't be possible. There are n squared variables, and you're giving me some small number of pieces of information. How would I know what the other numbers are? But in this particular case, this particular problem, if you could solve this problem, then you would get, then the reward was several $billion. So the normal approach, so the academic approach, by the way, would have been, well, obviously we can't solve this problem. Let's go find another problem, right? But the approach in industry was, obviously we can't solve this problem as posed, but maybe there is a way in which the problem is soluble and we should try to solve it anyway, right? So the industry people had it right. And I'll show you here how they had it right. So let's say, let's take that same set of data. I have Joe that I know doesn't like dark city and he doesn't like 0 dark 30. And I go down and I look at Sarah and I see that Sarah doesn't like dark city and she also doesn't like 0 dark 30. And in fact, they're giving exactly the same rating for these two. And I also noticed that Joe rated steel magnolias, but Sarah didn't. So I can take that one and I can put it here, right? And now I can say, and I know that Sarah saw Star Wars and Joe didn't. So I take that 3 and I stick it up there. And then I keep going here and I look at Fred and Jane and see that they actually are giving the opposite. They're anti-correlated. So one of them hates 0 dark 30 and steel magnolias. The other one loves 0 dark 30 and steel magnolias. Then I know that Fred loved Dark City and Star Wars, so I can predict that Jane will probably hate 0 dark 30 and Star Wars or Dark City. And I told you this problem was impossible. Hopefully you agreed with me just 2 minutes ago that this problem was impossible, and yet it seems like I solved it. And you can keep on going, right, for the whole. You can keep on going through this whole game and basically and make an argument for all of it. And this is actually the machine learning strategy, which is actually a really important. So if you're a youngster, super important to pay attention to the philosophical statement here. So the machine learning strategy is I'm given some problem that is not soluble, that I can prove is not soluble, right? And then what I do is I assume the problem is well posed and then solve it as though it was well posed. In other words, when you're given a problem that you can't solve, one approach is, as I said, the academic approach is to find another problem. The other approach is to ask yourself under what circumstances, right? With what assumptions would this problem be soluble, and then assume those to be true, right? And that's exactly what has been done here, right? So 10 numbers out of 20 was enough to determine the remaining 10 numbers in this example. What's really going on here, for those of you who remember singular value decomposition, if I have some matrix, I can write this matrix as so this is just an arbitrary matrix. I can write this in terms of a sum of what it would call rank 1 product. So I have a vector, a column vector times a row vector. So this gives me a little matrix. Column vector times row vector gives me a little matrix, right? And I can basically decompose that matrix into a bunch of low rank products. And what you really are saying, if you want to do this mathematically, what I just did by sort of seat of the pants, right, for filling out that matrix. If I want to do this mathematically, I want a computer to do this, then what you do is you say, take a matrix, and now imagine you can write it in this form, and then take all of the entries that you know in this matrix, and take only a few of these rank 1 products, and then do an optimization problem where you try to find out what is the best vectors here and possible numbers in front of them that will give rise to all of the elements that I have, and then use the minimum number of those in order to make the problem well posed. So so you can do this mathematically is all I'm telling you, right? So that actually allows you then to do that problem on a computer, right? Which is telling you that there are cases where a matrix might look like it has a lot of information, but it doesn't really have as much information as it appears it has, right? You can play the same game and here I'll just mention this sort of briefly in the context of the wave function, right? So what I just showed you was you could do this in general, and you could do that for the integrals, which we'll see in a minute. But you can first think about the wave function itself. And the wave function itself, the full CI wave function, that is the exact wave function, we can write in a form which has a matrix multiplying what are these are the exact details. These are not that important, but what these are is basically a set of orbitals that have spin up and a set of orbitals that have spin down. So fermions can be either up or down, right? And so we can take all the up electrons and put them into some product here, and all the down electrons and put them into some product here. Put those together, and you have a list of all the electrons and what orbitals they're in, right? And then you need some coefficient in front of that. That coefficient is that then can be, I'm going to label it CJK, and it can be considered as a matrix that is number of alpha orbital, a number of alpha strings, if you want, times number of beta strings, right? And the point is just that this is a matrix. So I've taken all those coefficients, I put them into a matrix, and then I can rewrite the, I can basically ask whether I can play exactly the trick I just played. So take that matrix and write it as a low rank construction of a bunch of outer products of rank 1 products of vectors. And the point is that you can, right? That actually this does work, right? So I'm just trying to give you the flavor of it. But this does work, and the effort now goes as it becomes the square root of the original effort of the problem. And the memory requirement becomes the square root of the original memory requirement in the problem. And I'll show you in a minute what that means. But the question is, does it work, right? So how many terms do I need? So what I just told you says you're going to figure out how many of these do I need. So how do I need the whole matrix or not? And the answer ends up being you need almost nothing. So here we're taking the molecule naphthalene and we're looking at the energy difference, the error that you make if you have only 1, 2, 3, 4 of those products, right, in the expansion for the singlet and the triplet energy of naphthalene. And what you see, this is in, you can't see here because of that, but what you see here is the error listed in Hartree. So chemical accuracy would be right around here at 10 to the minus 3. Is that with 50 terms, you have basically kcal per mole accuracy. Out of how many? Out of 10 to the 4. So out of 10,000 terms, you only need 50. Right? You need almost nothing. If you then ask about getting the difference, the singlet triplet gap, so the difference in energy between the singlet and the triplet in a bunch of molecules, similar acenes, then what you see is that by 15 you actually have enough. So that converges even faster, right? So you don't need very much. And what the takeaway from this is there's no information in the wave function. That basically, yes, sure, it has 10 billion coefficients, and most of them don't mean anything. Now you can ask about what does that mean for timing? Well, so here let's look at the time it takes as a function of the number of determinants in the wave function for a very, very good conventional full CI program. And you go up to like 16 electrons and 16 orbitals. That's 10 to the 10 determinants. And this basically is the slope is 1 as I could show you formally it should be. So the scaling, the time goes as the number of determinants, and the number of determinants goes as a factorial in the number of electrons, right? And we can now look here at this rank reduced scheme, this scheme which basically takes that coefficient matrix and writes it in terms of low rank products and tries to pick just low rank products as needed, and that goes as n to the 0.5, basically as the square root of the number of determinants. Right, so that means you're able to go up here to 30 electrons and 30 orbitals compared to 16 electrons and 16 orbitals on this time scale, which is a maximum of 1,000 seconds. I should point out that even these timings here, right, or the fact that you can do 16 electrons and 16 orbitals in less than 100 seconds is because of the graphics cards and full CI work. So this is already really fast. This is the largest full CI, as far as I'm aware, that's ever been performed by anybody. And so now you just want to get a sense of what we're talking about, right? So there are 10 to the 16 determinants here. So 10 to the 16 determinants, well, I was trying to get a good sense of what that meant. You know, the number of grains of sand on the entire Earth is 10 to the 18, or at least that's what people estimate it as, right? So the number of coefficients in this calculation, which takes less than 20 minutes, is getting it's within a factor of 100 of the number of grains of sand in the entire world. The amount of time that it would take to do this, if you take that calculation, you just extrapolate this out to 10 to 30, right, to where in order to figure out how long would a conventional calculation take to do that. The answer is 10 to the 15 seconds. And then I was kind of wondering how long is 10 to the 15 seconds. So started Googling around, and I found out that the age of the universe is 10 to the 17 seconds. So it's within a factor. So this calculation done in less than 20 minutes is within a factor of 100 of the age of the universe if we've done it the old way, on the fastest possible, on the best implementation ever. So now you would say, well, can I apply those ideas to the integral? So what we talked about was the wave function. I tried to show you how you can use take the electronic structure problem and the wave function and make things much, show that there isn't really very much information in the wave function. The other piece there were those integrals, those IJKL that were sitting around. And the question is, can we apply these same ideas to those? And here it's, there's a whole, some of you may know about this, there's a whole branch of art called shadow art. Right, so every instantiation looks very similar to what I'm going to show you here. But you see here a shadow, and you all know what that's the shadow of, right? So obviously, this is the shadow of this piece of junk, right? In fact, and this is the game, right? So the game in shadow art is to take some piece of junk and make it actually have a shadow that other people think they know what they're looking at. And the reason I show you this is because it helps you to understand what's going on actually in everything that I'm trying to give you a glimpse of. What's really going on is that you think because you wrote something down in some way and you looked at some structure and you had many coefficients, that this problem was really hard, but actually it's a different problem and you're just looking at a shadow sort of in the reverse, right? So you're seeing this, but actually then it's sort of the opposite problem, right? We see some shadow that looks very, very complicated, but the object isn't, right? And the next thing, the other reason to tell you about this is that this comes from changing the dimensionality. So if we think about the integrals, we could have taken those and just thought of them as a matrix, taken IJ as an index and KL as an index. But that actually is not really the right thing to do, because that's going to that folds the dimensionality in a way that will give you trouble later on. So what we showed, and here I'm just going to tell you the result. What we showed is that you can take this 2-electron integral, this 4-index tensor, and you can rewrite it in the following form, where you have basically 5 matrices that are being contracted together in some way. Right, and now that actually helps you a lot. So you introduce 2 new indices, right? So this matrix, this first matrix now has the index I that you had before, and some new index P. And the next matrix has this J index from before and a new index P again. And then K has K and then a new index Q and so forth. So there are 2 new indices that come in, but now every one of the objects is a matrix. So every object is a 2-dimensional tensor. These are being summed together to get this 4-dimensional tensor. Why does this matter? Right, so you might look at it and think that it's more complicated, but actually it's not. Actually, it allows you now to sum. Remember, what we're going to be doing is in electronic structure, what you would do is you would sum over these indices, those things multiplied by wave function coefficients. And now what we're going to be able to do is sum over this guy first, and then sum over this guy, and then sum over this guy, right? And so we'll be able to unpeel the onion sort of one piece at a time. And in that way, the scaling of the whole algorithm goes way down. So what this actually, the windup of this is that all methods that include double excitations, MP2, MP3, CCSD, CC2, these are couple cluster, these are all methods that people would use in electronic structure theory. All of those methods have their scaling reduced to the 4th power of the size of the system, right? Now then we should step back and remind you that the scaling of density functional theory, formally, which many would be familiar with, right, is the 4th power of the size of the system. And so what I'm telling you is that the scaling of all of these wave function methods, which are supposedly superior to density functional theory, is actually exactly the same as density functional theory. Right? And this, I can prove that to you, but it's so here you see it doesn't mean it's cheaper. Right, it just means that it scales the same. So as you increase the size of the system, the complexity goes up. So you can take proteins. This is ubiquitin, and do Muller-Flesig calculation, MP2 calculations, including dynamic correlation on proteins, and you can do this in a matter of hours. Right. So all right. So this now goes back to the beginning of the talk, though. What does this have to do with explaining with predicting anything? And what all this says is that it's going to be much, much easier to explain stuff. So you can do calculations faster, You should be able to explain things better. But what I told you at the beginning is that we really need to move away from that, or at least we need to add we need to add prediction and design as more routine pieces of the sort of workflow. So this calculation, which took 2 hours on 8,200 CPU cores, today you can do in 5 minutes on one workstation. So this is sort of and this is showing you the workstation that you would need at a different scale. If I actually change it so it's the same scale, then it's this big, right? So you have something like well, you have actually pretty serious speed ups, right? But now you say, what about prediction and design? I mean, he started out telling you about prediction and design, so I should tell you something about that. And and this is where you come into another idea, which, well, okay, if we can do calculations fast enough, then maybe we can start discovering new molecules. Maybe we can discover new reactions. So maybe we can actually take this method, which is because it's solving the electronic Schrodinger equation, it's able to have bonds rearrange and form. So it should be able to find reactions that we didn't know about, right? If we just drive it, right? And that's what we're going to try to do. So the basic idea here is I have some potential energy surface. I have some particular molecule A, and then here's my molecule sort of skating around. And you ask what's going to happen? Well, eventually, if the temperature is high enough, or if I wait long enough, it might go over this barrier from A to C, and I might get here. And maybe if the temperature is really high, maybe it'll go from A to B, right? So this is kind of what we expect to see. And what we know is that if the barrier is lower, so this barrier from A to C is lower than the barrier from A to B, so that means that this reaction should be faster. And so we think, well, we just go and find all the molecules and then find what all the other possible molecules are and what the barriers are, and then we should be all golden, right? But we won't be. And the problem is this, right? So the problem is that this makes it look like there are well-defined minima, but in fact, there are many, many, many local minima all over the place, right? And so we need to find all these, we can find these minima. These minima are molecules, right? And all these paths are reactions that are sort of going between the molecules. So we're going to need somehow to, so what I'm trying to get across is that the idea that I would take molecules, molecule A, B and molecule C, D, and find some path between them and discover all the molecules and discover all the paths is going to be problematic, right? It's going to be problematic because there are many, many, many paths all over the place here. Each of these waypoints is a molecule, if you want, on the surface. And so that's going to be problematic, right? So the number of species could be many. We don't know if we need to consider all of them, we're going to be in trouble. And the number of paths is growing even faster than the number of species. And so we need some other way, right? And the traditional way would have been to find the relevant species one at a time and find the paths one at a time. And we're going to try to avoid this. So the way we're going to avoid this is essentially by just running dynamics with the solving for the electronic structure all the time, so that all the chemical bonds can be made and formed. And we'll do that by putting this in some sphere with reflecting boundary conditions, and then we'll just let that run. And we'll let it run, and we'll look at what happens. And from what happens, then we will actually begin to catalog all the molecules that are built. Then from that, we'll actually catalog all the pathways, and then we'll build up a kinetic model from that. So this is an early example of what the dynamics sort of looks like. So you have, in this case, a bunch of acetylene molecules and hydrogen, and you just watch this thing go, and you can see that reactions are actually happening. So here I have now, this is now ethane, right, after the reaction happened. And so as long as the temperature is high enough and the pressure is high enough, then the reactions actually occur. When you find the reactions, you can actually say, well, now I have the different molecules, and I can actually see what the path was that led between them, right? And basically we have the computer do all the work of figuring out the what's actually going on. All right, so our first, we applied this to prebiotic chemistry. I will tell you just a few words about that. the backdrop question here was what happened in early Earth chemistry. So no one really knows what the early Earth looked like, but some people think it looked like that. But the question really is, where did amino acids come from, right? So where did biological molecules come from? And the Urey-Miller experiment was an experiment that was intended to try to figure that out, where they put water and methane and ammonia and H2 and carbon monoxide into a beaker, and then basically just put this in reflux, and they have a little lightning simulator that was going to basically do arc discharge inside here, and this would just run around being heated up here, cooled off, and then they would look in the trap and see what they found, right? And they did find that experiment was done many years ago in the 50s. And they found amino acids actually. So just starting from, remember what they started from. They start from water, methane, ammonia, H2, and CO, right? So basically nothing. Start from inorganic small compounds and go through that procedure, and you get amino acids. So we tried to do this, and the first thing that we found was that reactions reactions didn't happen fast enough. So you're still in that, which goes back to what I was telling you before. So the graphics card makes things faster, and tensor hypercontraction, which I was telling you about, makes things faster, but it doesn't make it fast enough. So we basically added in an artificial event generator. So we basically compressed the system so that things would run into each other. Because you ask, why don't things happen fast enough? The problem is that molecules actually don't. They're sort of kind of sticky. They kind of get next to each other. They stay next to each other. They don't, and it takes them a while to find a way to react, right? But if you sort of smash them together, then they'll react faster. And so you can have this sort of piston wave, or it's this periodic piston, and that actually makes the reactions happen much faster, right? So then you actually do many other things to make the reactions happen faster. I'm not going to tell you about them today. But then you can just ask, well, what do you end up discovering? So what we found were molecules that you might have expected: methanol, ethanol, various molecules that also are found in the Urey-Miller experiment, by the way, and then a number of biologically relevant ones, including some amino acid precursors and some really crazy molecules, and hundreds more. So we found hundreds of these reactions. Now, why does this thing, what's really going on here? Well, what it's really doing, it's not actually looking for molecules, it really is looking for reactions. And really what this is a way to sort of triangulate between two possibilities. So one possibility is that I would take every possible molecule I could enumerate. So I'll take the periodic table. There's no periodic table. Take a periodic table, find all the atoms, put them all, say I'm going to have 5 carbons, 6 hydrogens, 1 nitrogen, and basically, and then make molecules by enumeration, right? And then actually start enumerating reactions that could happen, right? And you could do this. That would be one way to solve this problem of generating the sort of a reaction network. The problem with that is that it would take you forever before you did any calculations, because all you would be doing is enumerating, right? There's so many of these that you wouldn't be able to get anywhere. The other possibility is to say, let's do a very realistic and very detailed simulation of the process. And the problem with that is that that's going to take a long time, right? So I'm going to have to actually simulate for a long time in order to see this. The advantage of doing this is that I would be able to actually read rates off of frequencies. So I could watch a reaction happening and say that reaction happened 5 times per minute. Therefore, the rate is 5 per minute. And you'll see in a minute, or you should notice by now, I can't do that with what I'm showing you, right? Here, you don't have any idea of the rate. Here, you would actually read the rate right off. But both of these are impossible because they take way too long. Instead, what we're doing is sort of in the middle, where we say, okay, we'll do some simulation which has some dynamics in it, which is kind of doing the right thing. We don't really trust the timescales at all. So forget about reading the rate off of the frequency, right? And that's actually what the nanoreactors do. So now you say, well, how do you connect that back to a real rate? And the way you do that is through something like transition state theory. So you take here an MD trajectory. So this is a piece out of that Urey-Miller trajectory, and the 2 pieces come together and they make some bond, right? And I can say, oh, okay, so I can take that as an initial guess for a minimum energy path that goes from a reactant to a product. right? And we can refine that, and you'll get something like this, which was showing you that was going from reactants to products. And then you can look at the energy along that path, and you have some pathway going from reactants to products through some barrier, right? And from that, you can put that into transition state theory and get some reaction rate, right? And one of the nice things is that you can kind of do, you can kind of go backwards and see where everything comes from. So you have some reaction, that reactant came from this reaction, the reactant here came from this reaction, and then this reaction, right? And you can kind of trace back where everything is coming from. Now, one of the things that is not always obvious here is that reactions can happen that you would not expect. So one of the reactions that comes out of the nanoreactor is a reaction that goes from the tautomerization, that you go from this guy to this guy. So the only thing that's happening here is that the hydrogen is going from the nitrogen to the oxygen. So if you know any chemistry, you look at that and you say, that's not going to happen, right? So the barrier for that hydrogen to jump off of the nitrogen where it's nice and happy, and then walk over through empty space to the oxygen, it's going to be really hard. The barrier for this is going to be super high, right? And in fact, it would be really high. But the nanoreactor finds this reaction, right? So then the question is how? And this is what it finds. Show you. So it finds a proton boost. And so just because there's a bunch of stuff in here, right? There happen to be some water molecules. And so it says, oh, well, water molecules could be in the right place. And turns out that the water molecule, to have two water molecules in the right place here is not that improbable. And so you find catalytic reactions. And what I'm trying to show you here is that even though you don't ever, you find reactions, and the nanoreactor knows, it will tell you that these waters are involved. So it will say, this species plus 2 waters gives you this species plus 2 waters, right? So it knows that those waters are in the reaction. But that means that this is not the same now. If you go back to the combinatorics, what you really need to be doing was, if you're going to enumerate all these reactions, you really would have to enumerate them with catalytic partners, right? And here it's basically finding them all without too much trouble. All right, so let's see. So I'll just say, just to try to finish up. So let's see. Okay, well, let's see. Sorry. Yeah, okay. Yeah, okay. So the nanoreactor is still going, right? We're doing lots of stuff with it. Let me try to finish here with one last thing and just say, then the next question that you think about is, how do I get molecules into this system, right? So you want your system to be easy to use, and you want it to be able to predict, and you want it to be able to design and all this stuff. So how do you actually make it that it's really, as what I've tried to show you, is that you're getting far enough along that you're able to actually use this computational tool in a sort of, in a discovery mode that you could pipe into prediction and design, right? And the question now is, well, how do you make all this stuff easy to actually do calculations? I mean, how long do you have to sit around and how do you make it easy to sort of make a workflow for this? So so all I want to show you here is you can then start imagining trying to use machine learning techniques to make that easy. And the way that we did this was, well, all right. I really just wanted to show you this. This is actually all I wanted to show you. So there is, you can actually download this on your iPhone. Basically, so what we did was we took machine learning techniques with image captioning. We made it so that you could actually take a picture of a ChemDraw sketch of a molecule, and it would actually turn that into a molecule internally, right? And then it would actually do calculations on that molecule to find molecular orbitals and so forth. And so you can take your notebook where you have molecules that you wrote down, and then you can start doing calculations on them. You can actually feed them into the nanoreactor, actually start accumulating, discovering reactions with those molecules. So the app is called MOLAR, M-O-L-A-R. If you look for it on the iPhone, you can find it. So that's super cool. I should have spent more time on it, but I didn't have time for that. So let me just finalize this. I think there's several things I was trying to tell you. There's several ideas here. the first is to really realize, video games have driven really theoretical chemistry, which is a little unexpected. That ideas from machine learning and artificial intelligence, including these recommendation systems and so forth, are feeding into more efficient and accurate ways to solve these chemical problems. I think that routine prediction and design at the molecular scale is something that we still need to be pushing for, but I think it's actually on the horizon. I would not say that we've done it yet, but I think it's actually coming. And automated discovery approaches like the nanoreactor are really, I think, going to be an important part to that. And you imagine that eventually this is, and some people are thinking about this, but more seriously than we are. But eventually you can combine this with experiments, and then you really would be able to automate chemistry. And that's sort of where I think all this is going to go. So let me acknowledge the many people that did this. It's been done over quite a long time. From this has elements that go back 10 years. And so there's been a whole bunch of graduate students and postdocs that have been involved in this, and many people funding it, from NSF to the Navy and Department of Energy and a number of companies. And thank you for your attention, and thanks again for the Thank you.
I remember, I think the first time I visited Illinois, you were just getting started with the GPUs. It's been a long journey. But
yeah.
It's really very exciting. If you don't mind repeating questions.
Sure. Okay. Sure.
And what here.
Yeah. Yes, you do. You get memory and time complexity advantages. It's called tensor hypercontraction, by the way. But in any case, that and hypercontraction is because you actually are. If you might have noticed that there are indices which exist over 3 objects, and you have to sum over all 3, which is like a Hadamard problem. But yes, you do get memory savings as well. The best thing to do is actually, I didn't tell you about, it's even more complicated, but you can take that same idea and you can sort of play it on itself, right? So you essentially say, the way I showed you the idea, it sounds like you have to actually find the object, the complicated object, and then decompose it. And I tried to suggest to you, oh, by the way, did I forget to repeat the question? I did. All right. And I tried to give you the impression that you could actually take the object and find its decomposition without completing it, right? So you would find it sort of piecewise until you got close enough, and then you would forget about all the riffraff at the end, right? But you might actually get even more greedy, and you might say, I don't want to ever know the object. I want to be able to sample the object and construct the low rank piece directly. And so we showed how to do that for a couple clusters. Essentially, you solve the equations in the reduced space directly. And that means that you lower the memory even more, right? So you never have the full object at all. So. Mm-hmm. Yeah, so the question is whether the question is whether there is an analog of folding at home for this kind of technology, and the answer is that there should be. I didn't tell you about that, but that's one of the things that we've been pushing on most recently, is trying to find ways to take many of these, to basically make it very easy to do these calculations at scale, right? So where you do thousands and thousands of the nanoreactor, for example, there's no reason why you couldn't be doing many calculations. In fact, you have to, but they're all independent, right? So all of those little reactions that you're doing, take some reaction vessel and then heat it up and smash it around and see what reactions happen. The information that comes out of that is the reaction, the molecules, the reaction, and then that are then going to be subject to future refinement, right? The refinement itself, these are all independent. So you could do something like folding at home. We're not trying to do it in the distributed computing way where we have people give us their graphics cards, although maybe we should think about that. We're just trying to be able to do it in a way where if we have enough graphics cards lying around, right, or an AWS or something, we can just spin up however much we want and let it do compute and then spin things down. It's a little bit easier. But if we could get people to give us their graphics cards, that would be that would be good. Well, the most interesting thing was actually in the context of it's an antioxidant. There's a class of molecules called radical trapping antioxidants, which will catalytically actually take a radical and catalytically remove radicals. Is basically what they do. And so in that case, we actually discovered a mechanism that was, as far as we could tell, new. And then so it was surprising, right? So there's a mechanism that actually looked at it, so that's kind of odd. But then it turned out, and so I don't know whether this is it was annoying to me, but I'm not sure whether I should be annoyed or not. What we found out is that if you dig in the literature far enough, right, then you find out that yes, this mechanism was in fact actually suggested, 20 years ago in a context which was almost the same, but which didn't have the aryl group, an aryl group, and so then I'm not sure that just put me in. I didn't know what to say because I'm like, okay, we didn't know about it, so I guess it's a discovery for us. This shows you that it's actually reasonable, but it also means that it's not actually discovery. And so then you're getting into, and so the reason I was telling you this is that you get into this kind of funny thing of how do you know when you're predicting or not? Because maybe you predicted it, but it was already known before by someone else. And I'm not sure how to deal with that, right? So I'm trying to figure out mostly I'm trying to figure out how do you, this is answer a slightly different question, right? Which is trying to figure out how do you actually know whether you're really predicting and designing or not. But we did find a new mechanism.
And there's the whole generation of organic chemists who just
right.
have this
Yeah,
brainful
sure.
reaction and
Right,
this
sure.
intuition on it.
Sure.
Seriously,
Sure.
computational chemists just
Yeah.
don't have that, and so
Sure.
That's another piece that
Yeah.
if the machinery can find those reactions,
Right.
that's actually an interesting result in
Right.
itself.
That's right. That's right. There's another piece. Well, anyway, yes, that's right. I won't say anymore. Mm-hmm. Mm-hmm. The problem with transition metals is that their electronic structure is so nasty. So, but anyway, I'm sorry. I didn't want to stop your question. Yeah. Yeah, there's one thing that, yes, and we don't. Then that's so. So you're pointing to it. So I think what your question is whether or not they some of these sort of rank reduction ideas would help you to understand how to actually improve density functional theories. I think what you're asking, or at least something like it. Yeah. Right. 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 And I think so the answer to that is yes. That's one of the reasons why. So I didn't actually show you, but we used this tensor hypercontraction in the context of multi-reference perturbation theory, and there it does make things much cheaper. The scaling of multi-reference perturbation theory is essentially the same as the scaling of Hartree-Fock. It's just multiplied. The cost is multiplied by 100. But as for small active spaces, as active spaces get large, then the prefactor gets higher and higher. And the part of the reason that we were doing that was because my impression is that a multi-reference perturbation theory is the only thing that you could really trust for transition metals in cases where you have changing, you're not saturated, right? So, but we're not at the stage yet, unfortunately, where we do that for large enough active spaces routinely enough. It's still expensive. So it's still more expensive than DFT. And so I'm trying to, what I think is the right thing to think about now is how do you, and other people are thinking about this problem too, how do you actually take some of the ideas that, the simplification that DFT has and graph them onto a wave function method? And if you look at some of what I was showing you briefly, you could start to imagine that the reason why DFT works is because of the rank reduction types of things I'm showing you. But it's a nonlinear form, right? So it could work even better, right? But if already in the linear form you can do this kind of rank reduction, there might be a way to actually combine these things, and that would solve a lot of the problems. Yeah. Not yet. Yeah, not yet. But we definitely are thinking about. Definitely, that's the next thing to do. Whether I'm not ready right now to ask for experimental lab space yet, but and my own experience in the lab has not always. But yes, that's so one of the things I didn't tell you about is coupling the nanoreactor to sort of template driven synthesis planning, right? Which is, so we've been developing synthesis planning systems, and then where basically you just take templates for reactions. It's sort of like the expert system approach to trying to understand how to do design of reactions. And the reason that we were interested in that was precisely to connect it with the nanoreactor and then start actually being able to suggest new reaction types and feed those into that system and take the reaction types, and then for instances with given R groups, for example, start predicting what the yield would be or the rate, and then and that you would then really want to connect to an experimental system, which then you would have some sort of feedback where you'd effectively have the sort of AlphaGo strategy, right? So in AlphaGo, the way that the machine learns how to play Go is by playing itself, right? And so this is what you really want here, that eventually you get to the point where you have some system that is able to learn chemical rules and it's able to predict things, and it is able to test its predictions, and then it's able to find out that it failed and then to update its own system, and that would, then you wouldn't need chemists anymore, right? Then you'd really do design, right? But yeah, Well, I don't know. I don't know. I don't know. I don't know. I might be. I mean, maybe I'll. Maybe 10 years from now, you just look back and laugh and say, "How could you have thought that any of this could possibly work?" But I think it might be. It might be that putting things together might not really be any different. It's a little extreme, but it might not be as much different from screwing together two parts as we think. But we'll see. Right. Yes. 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 Yeah. Yeah. I had intended to tell you something about photochemical nanoreactor. Actually, we've done this. Things are more complicated there, but we have done that. You essentially have the same kind of discovery sort of approach, where now what you're looking for are conical intersections and basically trying to make maps between them. And that I would say it's in its early days, but it's working, right? For microwaves, we haven't tried. I mean, that shouldn't be that different. Some of the schemes that, but I don't know enough about microwave. I thought microwave chemistry was mostly about temperature hotspots, but maybe I'm wrong. And so yes, so the answer is yes. We've done some things, some of them we haven't done, but definitely those are things that are on the agenda. No. Mm-hmm. Mm-hmm. Ah, okay. So the question was, let's see, the question is whether the summary of the question is whether the paucity of information is system specific. So the answer to your question is no, it's not system specific. It's quite general. But now I have to say we have to actually ask that question. We have to be slightly a little more rigorous with the question, right? So if you were to could you design a molecule which would break these approximations? And the answer to that is yes, you can. Right? So you could design a molecule whose electron, I don't care whether it has I don't care what, it's just a wave function. I could write a wave function that can't be decomposed like this. And then I could back out some Hamiltonian, which gave rise to that wave function. So I'm not saying, when I say it's general, I'm not saying there's no way to break the approximation. What I'm saying is that every single molecule we've ever looked at, it works, and we've tested a number of them. And it seems plausible that molecules in normal states, right, so that are near their ground states or whatever, so they're not where you haven't broken every bond in the molecule, are very likely always actually describable in this way. But it's hard to prove that, right? So my answer is it's general as far as we can tell, but we know you could break it. But we know the cases that you would use to break it are in fact the same, have properties that make them super, super weird for molecules, right? It would be like super fluid super fluidity, being like in very strongly correlated electron liquids, and they're not where molecules usually live. Yeah. Right. That's right. Right. That's right. Yeah, that's right. That was the other piece of your question. So unlike Netflix, you actually know here because you basically can just, well, first of all, if you had all the object and then you decomposed it, then you can just decompose it better, right? You know, you can tell how good your decomposition is. That's actually something I didn't point out, but I should point out. So machine learning is kind of getting, growing in interest, right? And what was actually done with the Netflix problem, if you sort of step back, is that we took machine learning ideas, we used them to learn something, and then we didn't bother to learn at all. We said we know the structure, right? And so we learned the structure, and then we use the structure, and we use it in a way where it's self-correcting. So it doesn't make any difference in that context. You could do that with a neural net too, which we're kind of playing around with. In this context, it doesn't make any difference whether or not your learning had enough data or not, except that it needs to have enough data to show you the pattern. But it didn't matter whereas most things you actually you have to worry, am I just memorizing data? Am I overfitting, right? Whatever. Here you don't have to worry about that because the machine learning ideas are really helping you to see how to recast the problem. And that's a different strategy, which I think I don't think it's so easy to pull it off, and to repeat it. But if you can do that, if you can play that game, then you're going to be much better off. You never have to worry about whether I have enough data to train my neural net. You never have to worry about whether my neural net is overfit, right? You don't have to worry about any of that. So.